working this time. If there is somebody, no YD, if somebody can have a look. Otherwise, right? Nobody. Since the action plan is full, you could start.
Okay, so we start. Okay, so welcome everybody. This is the 100th IETF, and it's my first one as a co-chair. So Vincent and I are very happy to have you here. And we have a very, very full agenda, actually. And maybe you want to put it? No, you want to put the disclaimer first. Okay, so this is actually a very important thing. You probably do not know, but there was a meeting yesterday of all the chairs for the research group, and actually the new rules for IPR was discussed. So I think it's very important if anybody presents something today that has IPR issues, please make sure that you are compliant with the rules.
Yeah. The rules are compliant with the previous ones, but with some clarifications for a few changes. We can talk about it later on.
Okay, so Administrivia, we have updated the charter of the group, and I'm going to continue. I'm going to mention what we did. The wiki is available for uploading documents and things that you think are valuable for the group. I intend also to use it to upload documentation and background papers that have been published both in industry and academia in this field, so that people have a good image of what is happening in the field.
I would add that this is the right URL for the for the wiki. Sorry, there are a few wiki links on the various web pages for the group, data tracker and IETF, that are not working. We will fix it, but in the meantime, this is the right URL for the group.
Mailing list is there. The slides about this are the ones that we have already been uploaded. If there are presenters who did not send us their slides, please do it now. And there's presentation. So what I said is that I don't intend to go on with a lot of this. The agenda is very, very full. I think we were very happy that we could get that many presentations. So we're going to go to coding, use cases where network coding can be beneficial. And next slide. And the research projects update and things that are ongoing. This reflects, all these presentations reflect a little bit of the new directions of the group, and that's the next one. So we have one draft that is actually in awaiting the end of the review. This is a taxonomy, the one that has been essentially being worked on for many years, and finally I think we got a good agreement. In the individual ideas, we have something ongoing on network coding and satellite, which is also going to be presented here. We have a network coding for ICN that, again, will be presented. Vincent is going to present the API, and I know that there's a bad name for the quick one, but we have the presentation from Google on FEC for quick. So what's new? I wanted to put something with color for once. So what's new is because we changed the name, and the reason that we changed the name has nothing to do that we changed the fact that we're talking about network coding, but a lot of people didn't really know what network coding was used for. So we changed the name so that people would know that when we do network coding, it's actually to have more efficient network communication. And it is part of a toolkit for improving the performance of communication. And this is the goal of this group, is to look at coding as part of this toolkit for improvement. We have a new charter. Why do we have a new charter? Because the old charter was about 5 years old. And since then, there's been a lot of development. And I think it was also to reflect the fact that we wanted to move a little bit from just codes and things that go directly on codes on more into how are codes being used or could be used, since we are a research group, and what are the research area that should be investigated in order for codes to be better used or better applied in, again, to improve the efficiency of networks. We have a new milestones, but it's on the next page. So what we did in the meantime is we had an interim meeting in Boston on September 19th, which happened to be my daughter's birthday, so it was fantastic. We had way more participants than we thought we would have. Actually, we were extremely pleased by the number of participants. There were 10 to 12 people local, depending on the time. There was more than 10 online. We have to apologize because the online, we were using a WebEx version that did not work very well. So a lot of time the WebEx was going up and down, and I guess next time we're going to do better. But the goals was essentially, we had started working on the charter at that time, and we wanted to have the feeling of the group to define the major groups, the major goals that we want to achieve. And again, this focus on the research on how to use codes as a toolkit as part of the toolkit for improving efficiency. Also look at common issues. What are the big elephants in the room? Why aren't the coding solutions being more used or being more applied in the industry and in the research also, and the challenges that we need to address if we want these things to go better. So essentially it was a great outcome. So we had a proposal for a new charter, a new milestone that we sent to the list for approval. And actually we had some discussion and add-ons, and we actually identified a number of activities and the first volunteers for doing these activities, which I think most of them are here. So it was a very successful meeting, and it made us think that we're going to redo that. And by the way, we felt that Boston was a good place to do it because it seems that there's quite a good proportion of researchers in the field that are in the Boston area. So the milestone that we identified and now uploaded, we want to look at a document talking about existing solutions. Again, this is something that, although this group has been chartered for quite a long time, there's never been a document saying what are these things and what are they used for and why would we want to look at them. We were going to look again at this idea of network coding in Quick. Quick had FEC from the beginning. Can we make it better? There is a NC and satellite use case to look at an overview and the research challenges when using network coding over satellite networks. And we have Angelus here, and we have Nicholas Kuhn, and we have Emmanuel, who have all looked into these things. We want to look at some kind of a common coding API. The reason for this is that we know that there are codes. There are codes that people are using. There are codes that people may use. There may be new codes. And what we want to be is future-proof, so that coding solutions that exist now, if we want to use them, but something better happens later, that we have actually some way of being able to change the code without changing the whole code again, but in the sense of software code that support it. Some adoption challenges, why isn't this not being used? A big elephant in the room that has been there since the beginning of network coding in the IETF is the network coding and congestion control. There's been more emails and stuff on this that I can just think about. And is there a way to finally get this behind us? And actually, this is also, Michael Welser is not there now, but this is something that could be done also in collaboration with the ICCRG. The ICN use case, again, we're going to have a draft on this. This is something that has been going on for quite a while. And we have also the people from the ICNRG, and we had talked about doing maybe common meetings at one point. And there is the last one for the moment, doesn't have a draft, but there was this idea of having NC and robust tunneling. And I can tell you that after attending the TAPS meeting yesterday, there could be some reuse of some of the work that's been done in TAPS to do this. And Allison has a question.
Allison Mankin, as the IETF chair. So I took the word use case out of all your milestones,
Okay.
because I think it's important to not do a here's an exemplary thing, but to do a here's a hard problem that we solve for these people, right? And it might be that in the end you'll consolidate these documents because you've solved some hard problems for multiple types of use. So it's quite important not to publish. They're a little ephemeral use cases, right? Because they're exemplary. They don't actually necessarily last for very long. And also, I now have some fuel for this, so we're going to work this in the whole IRSG. They cost, the documents are quite expensive in the RFC editor, so they really want us to use our RFCs well. So I see it all there, and since I'd taken them all out of all the milestones, I thought I'd take this moment to explain the kind of goal we're looking for, which is solve a hard problem, and then see how to make it to the.
And I agree with you. I think if we just say NC and quick.
Yeah, you don't have to say
NC and ICN.
Yeah,
we don't need to have the use case.
Right, and then it may turn out that several of those things turn into one document, and I think all this is very explorable by your group, especially since you're now having so much more energy.
Okay, thank you. Okay, and again, so well, again the tabs. So another thing, and now you're going to talk. So we're going to think. Something that has been an issue for quite a long time also is people come here and they're new in the group and they actually have no clue what we're talking about. So what is a network code?
Yeah, so we prepared a very brief tutorial on this topic, just going through the IDs, main IDs, and not into the details. So.
No, but attends, je vais les changer.
No, it's okay.
So we did the cat is for you, Alex.
Okay, so so there is a cat. So this is an extract from the current taxonomy document, which explains what we mean by source coding, network coding, channel coding, physical coding, what we're talking about in this research group. So it's quite usual, but network coding is the thing in the middle. On the top, you have potentially source coding. Source coding typically is, multimedia encoding, multimedia decoding, all these source-specific stuff, which depends on the application, of course. And at the bottom, you have, of course, those physical layer FEC codes. That's one way to have network coding in this protocol stack. The other way is putting this network coding stuff built within the communication layers. So below UDP, below IP, below TCP, depends on what we want to address. There are several ways to do that, but just to make it clear. Then there are a few things we want to do and a few things we do not want to do. More particularly, we will never consider physical layer stuff. Physical layer codes, bit error correction, bit error detection, all of this is physical layer specific and will not be addressed within this research group. On the opposite, we want to deal with packet losses. So packet means many different things. It depends on the context. It can be a UDP datagram. It can be a UDP datagram payload. It can be a IP datagram itself, TCP segment, whatever you want, an application message, and so on and so forth. So it really depends on the context. Yeah.
Just quick clarification. Is that just another way of saying you only do erasure coding or erasure?
Yeah.
And so I'm trying to think, if you get a packet and the packet CRC is wrong.
Yeah.
All right.
It's removed.
Is that treated as an erasure or do you actually try to correct that packet?
We don't try to correct it within the network.
So you're using these terms the way I would say erasure codes.
Okay, we decided to keep it simple, so we removed erasure and we use loss, but there are synonyms.
Okay, loss would be fine, but you didn't say it here either.
This is the last item, yeah, packet loss or packet erasure. But you're right, maybe we should also remind that erasure and loss is the same in our context.
And by the way, we will also probably add the fact that there were comments from the Steinwerth team that maybe also we wanted to talk about using coding to reduce state in the network.
Yeah.
But for the sake of this presentation, we decided to limit it to like the most often used usage of the coding. But I'm taking a note on the erasure.
Yeah. So, thank you. Okay, so the vocabulary is a little bit more complex. I don't want to make it complex, so I skip the details. So I won't speak about symbols, for instance. So next slide is about coding basics very easily. Well, you can have packets, source packets, repair packets, and the typical way of doing that, encoding, consists in computing a linear combination of for instance, source packets into repair packets. So you, in the first case, the first repair packet, you just do the XOR sum of the source packets. This is one way to do that. Another example just below consists in multiplying each source packet by a certain coefficient and doing the XOR sum of all of these. Well, it's pretty simple. Of course, you can also, and in some use cases, you will also compute repair packets from other repair packets that you have received. This is another way to do that. And in this bottom example, you can see that we multiply the first repair packet by coefficient 57 and second repair packet by another coefficient. You do the sum, the XOR sum of the two results, and you produce your additional repair packet that you can send on the network.
So I think the big message of this thing is it's nothing else but an algebraic operation. It's nothing really.
Yeah, it's very basic.
It's not rocket science.
Yeah, it's not rocket science for sure. You basically have two mathematical operations, XOR. You have two data chunks, you want to XOR them, and you have also this multiplication by a coefficient. You multiply a certain data chunk by a coefficient over a certain finite field, but there's nothing complex in this operation as well. So that's almost what all you need to know in order to be able to understand at least the main FEC techniques used in this domain.
Are there any questions?
Now, we have two kinds, basically, roughly speaking, we have two kinds of FEC codes or network codes. One of them being block codes, the other one being window-based codes. So block codes are traditional codes in some way. You probably know some of them by name, Raptor codes, Raptor Q codes, Reed-Solomon codes, LDPC, LDPC stack S, all those are block codes. And here the idea is quite simple. You have this continuous packet flow, and you segment this continuous data flow into blocks of a certain size, most of the time of the same fixed size, and you do FEC encoding of those packets in this block, and produce one or more repair packets to protect this block, and you continue like that. So that's the basic solution, the one that has been addressed by the RMT and FakeFrame IETF working group, for instance, in the past. Next. And then you have this second approach, which consists in considering a sliding encoding window, a window that will slide over the set of source packets or repair packets. It depends on the example. I'm considering source packets only. You have this encoding window that slides over this source packet, continuous source packets. And whenever you need to reproduce one or more repair packets, it's pretty simple. You consider all the packets in the encoding window. You compute a linear combination. You produce one, you produce one repair packet. If you want more, then you consider another combination, linear combination, and you produce additional repair packets, as many as you want. All of them from this, for the current encoding window. So that's pretty simple. Back. A typical example are, well, the well-known RLC codes. RLC codes, the ones that I'm working on in the context of TSV-WG. I will come back on this later on. Fulcrum, BATS, there are additional examples, but those are examples of codes that typically work in this manner. Then, there are additional names for those window-based codes. So it's more or less the same. Sliding window codes is more or less synonymous. In the case where this sliding window is not of fixed size, but can evolve over the time, depending on, for instance, feedback that you may receive from the destination. This is an option. It's not always the case, but if you have some feedback, you can adjust this window size. And in that case, you will talk about an elastic window size code. On-the-fly codes are more or less the same. So main benefits compared to block codes is, first of all, it's much more flexible. And then it's also very beneficial in terms of reduced latency. So when you have very time constraints flows, real-time flows, then it makes sense to use this kind of codes. Next. And that's more or less all I wanted to say for this tutorial introduction part. We have this taxonomy document that explains or defines additional terms, and well, single flow encoding, multi-flow encoding, all of those are defined in this document. You can have a look at it if you need. We can also talk after the meeting, no problem. Next.
So now I have two additional slides to give you, to browse a panorama of what has been discussed, presented in the past within this research group. So the first slide is about the codes themselves. So we talked a lot on about RLNC. This is the historical codes for this use case for network coding.
RLNC, by the way, is for random linear network codes.
Yeah, I forgot to mention that. So random linear network codes. So the coefficients are produced randomly in that case, and they're also transmitted within the packets itself in order to be able to do what I mentioned after, in order to be able to do re-encoding within the network. So that's more or less mandatory to do that. I simplify a little bit. But there is no specification for the moment for those codes. So this is probably something that is missing. Next is the fulcrum network codes. Fulcrum network codes was proposed and introduced by Steinwurf a few IETF meetings ago at Hawaii. Yes. So you have the slides in this URL. BATS was also introduced and proposed some time ago. It was in London, if I remember correctly, by Professor Raymond Young. So you also have the slides, you can refer to that. There is no other specification for those codes. And you have this work in progress about RLC codes, random linear codes. It's in fact more or less the same name, but it's different. The main difference with respect to RLNC is the fact that they are only for end-to-end communications. So you do not carry the coding coefficients, for instance, within the packet itself. You just carry an identifier, a seed for a PNG. It's work in progress, and well, it's progressing well, in fact. So you can have a look at the document. So the next slide, this one is about the protocols. So the codes themselves are not sufficient. You need to have a full solution. That is to say, you have to specify also the mechanisms that will be used to make all of this work together. So basically, you have three proposals that have been discussed in the past. The first one being Tetris from Iso Superhero. There is an old specification. There is this internet draft that is now expired, but maybe I hope they could be resubmitted, updated. It's up to you.
It's the benevolent dictator thing. We would like to have it.
Okay, so most probably it will be updated soon. Then we have this Dragoncast. Cedric, at the end of this meeting, will say a few words about it. This is another way to do to apply network coding, and this time with re-encoding within the network. So Cedric will talk about it with a specific use case. And there is now also an expired internet draft that describes what it is. And finally, there is this fixed frame extension. So fixed frame is already specified and standardized. This is IFC 6363. It was 4 or 5 years ago. Now the idea is to extend it in order to be able to use sliding window codes. It was restricted to block codes. So we extended it for sliding window codes. The specification is more or less ready for working group last call, so it will soon be moved forward. Next. I think this is all I wanted to say. Just to conclude, well, there are many research outcomes in the domain, the field, very interesting outcomes. Here in this group, it's time to transition to application and protocol research. And this is the main goal of this group. And of course, doing that in collaboration, with a close collaboration to other research group or IETF groups, whenever it makes sense. So we'll see examples today afternoon of collaborations. That's all. Questions, comments? No? Okay, so I will continue with... So second presentation for this generic API now. So the idea is to have a... Can you next, please? So this is joint work with many people, with Jonathan Detchard from Iso Superhero, with Cedric Hadji from INRIA as well as me, just like me, but we are not in the same team. With Jan Sweat from Google and with Morten van Pedersen from Steinwurf. This is work in progress. So the idea of this work is to specify a common API for the coding part and only the coding part. So this is this bottom right box. So typically this generic API will make it possible to interact with the codec itself by doing session management, initialization, initialization, teardown of a codec instance, for instance. You will also be able to interact with the codec in order to specify and manage the encoding and decoding windows, in order to specify and manage the coding coefficients. So it depends on what code you are considering. Sometimes the codes are generated by the codec itself. Sometimes they are generated by the application on top of the codec. So there are several ways to do that. You also typically have functions to do FEC encoding and functions to do decoding by submitting new repair packets or new source packets that you may receive from the network. So that's basically the goal of this API. And this is, I will insist, really a low-level API for a low-level component of a much larger software. So not in this API are all those functions that are typically on the protocol side. So congestion control, memory management, transmission, reception, packet header creation and processing. All those are things that will be managed outside of this codec. So they are not in the API. Next. So we are talking about a generic API. So why is it generic? What is generic in this API? Well, we want to have something that can be useful with many different codes. So not just one code, not just specific to one code, but generic with and usable with different codes. We also want to be able, well, initially I had in mind being able to have an API that is common to block codes and sliding window codes. It turns out that it would make the API a bit awkward. So I think it's preferable to remove this block code support and only focus on sliding window codes. But still, this is something we can discuss. If you have an opinion on this, we can talk about it. Then MDS, non-MDS makes no sense in this context. We want to be able to produce as many repair packets and manage as many repair packets as we want. So this is what we mean by rateless. We have this feature typically. We also want to be, and this is very important, with both codes that can do re-encoding within the network or codes that are limited to end-to-end coding. And it makes a few differences in the API. We have to manage this. Next. Okay. The goal is to simplify codec development on one side and also simplify protocol and application development on the other side by having this already standardized and specified API. So it makes codec development simpler because typically designing an API, you can believe me, is something complex. It's not obvious at first, so that's one part. And of course, if you have this common API, if you want to test new another type of codec, then it will make things much simpler from a software development point of view. So that's very important. So we also want to ease benchmarking, facilitate benchmarking. You can more easily swap between several codecs and test which one is the best, is most appropriate for your use case with this API. We also want to simplify the development of a future open source codec. I will talk about it at the end of this presentation. Also because it's feasible, which is also a good reason to do that. So the internet draft, yes, question, Dave?
This may be a little too detailed here, but because I did some work in this area, I'm just curious what your thoughts are. What if the core of the codec is in an FPGA?
Ooh.
And that FPGA, and you need the data to stay in the gates of the FPGA, for example, because the next thing you're going to do is crypto.
Okay, good question. This is typically something we'll have to discuss, but outside this, because I don't have any experience on this domain.
Maybe getting the actual bits in and out across the API, and you may not want to do that.
No, that's a good point. That's a good point, but I have no experience, so we can discuss this. If you have an idea of the requirements and the specificities for this use case, then I would be interested. A good point. Okay, so for the moment, if you look at the internet draft, there will be, you will see that there are two APIs specified. Well, just a list. We just list the function. We don't try to do anything more intelligent. There is a third one that is available at this URL from Cedric. And of course, we expect something else from Morten. And I don't know for Jan, but we will talk about it later. And the next step, typically, is to identify what is common, identify what is different, well, work on this in order to find the best solution, I would say, for this generic API. So that will be next step. And finally, yes, I mentioned the idea of having and developing an open source and a free reference codec. So once we have the API, we can continue with this codec. This will be next step. Well, typically C++, we'll see for the FPGA. That's a good point. We are looking for candidate codec that may exist. We know that Cedric has one proposal, this Gardinet project, which provides already the functionalities that we are looking for. It is a little bit specific to embedded platforms, but it can be as well a good starting point for this development. So if you are aware of codec, open source codecs that may be the basis for this work, then do not hesitate to tell us. And that's my last slide. Yes. Yeah.
Ian Sweat, Google. I had a suggestion that on next steps, possibly it would be certainly very useful to actually try using multiple of these in a certain environment. I mean, given now that you have 3 already that appear to have the same API, actually try them in a real world use case and make sure that the API is like not overly cumbersome to use before you implement 5 or 10 of them. I mean, obviously. We'll see what that is, but I mean, that definitely, it's always good to make sure your API is like easy to use. I mean, that was a major problem with, I know this is a totally different area, but like the TFO API in Linux turned out to be like stupidly difficult to use in V1. And it caused a lot of people not to use it for like 5 years until they fixed it. And then the Apple folks like did the right thing, but yeah. Yeah,
the experiment, we typically need experimental developers to do this work. But if I mention those 3 APIs, it is because behind them, there is actually running code, and we all have some experience. We know that some features are maybe could be improved within those APIs. So we want to benefit from this experience, this common experience, in order to make something that is useful and efficient. Yeah.
One further suggestion, having tried to benchmark things like this, is that it'd be really good to have a null codec, so that you can measure separately the effects and the inefficiencies of the API compared with the effects and the inefficiencies of the codec itself.
Yeah, sure. Typically, memory management is always an important aspect from a performance point of view. If we can avoid copies, it's much better. More question? No? It's okay?
Okay, so
thank you.
So the next presentation is the satellite people. So it's Nicholas and network coding for satellites.
Hello, everyone. So I will present an update on the draft on network coding and satellite. I don't know if everyone is aware of the goal and the scope of this draft, but I think that with what Vincent said, we have good insight. Basically, we have had lots of activities in network coding and satellite over the past, lots of research activities going on. And the main idea is to try to identify what is actually deployed at the moment, and if there are any interest for research, different research axes to further make research on that, but also having in mind that we have to make that into products tomorrow. So basically identify challenges where we can actually have marketing, when it makes sense to actually deploy these techniques, and what are the challenges in deploying them. Next slide, please. So as opposed to what we had in the first draft, we have improved the presentation of the notation and what we can have as a generic satellite, multi-gateway satellite network, because the main problem in the satellite industry is that we don't have reference architecture for multi-gateway net systems like you may have provided like it may be provided by the SWIFT-GPP or Broadband Forum or this kind of thing. So there are some standards, but it's not enough to make things interoperable. So we just here propose some notations because sometimes the words we would use in the following of the draft may not be clear for everyone. And for the moment, we have just gathered some of the keywords we are using. But depending on then how the use cases and the needs of the description in the use cases, we will describe use cases. And then depending on what we actually need in the description, we will remove and update. Also, that is some note for myself and for you is that basically one of the main use cases we want to focus on is when we have mobile user, when the channel capacity is highly varying. And in these cases, it's very difficult for physical layer codes to actually cop from the errors. And in these cases, we think that it's very important to deploy some network coding schemes in actual deploying systems. To better match this document with what is done in the working group, we have tried to take the taxonomy draft and make some kind of matrix, because basically what Vincent presented earlier was the different layers at which the network coding can be applied, either physical, packet, network, source coding, and then the different ways of doing it, either end-to-end, network coding, or interflow, single path, multiple path, to better see to try to make, for each example of what is deployed today, to see if there are any gaps and opportunities for more network coding. And that table would be further fulfilled by the use cases. So the idea is to see if we can actually use the taxonomy to be the base for the organization of our use cases and identification of the need for further use case. So for example, here, the problem is that maybe it's because I didn't understand that correctly. But when we have, for example, video streaming like YouTube with Quick, we have some, I thought it was the source node, but now I understand that the source node is actually the video encoding the thing, not the transport layer. But in Quick it's somehow mixed at the moment. But basically it's more, basically we have things that are done end-to-end per flow and single path. And what is done at the moment in satellite industry is to introduce coding at the physical layer. So this is what we have, we call physical layer frames, and for which we have only coding at the physical layer. And there are probably some points that are missing here. So the idea is if anyone knows things that we are missing, please tell us. But we think that there's nothing much on the multipath, the network coding and the interflow coding at the moment, and not much at the packet and UDP level neither. So that illustrates the opportunities. And next, please. And don't hesitate to stop me if the time don't. Thank you. Basically, for the moment, we have 4 research axes. So we have proposed them. If anyone wants to collaborate on that, we are open to discussions and share the work on describing these use cases. This is what some of them we are more believed in. For the moment, we just listed to see if there is an interest for other people. We have our own preference, which I will hide at the moment. But basically, we have that is something that has been demonstrated already. The two-way relay channel, when we have 2 terminals, satellite terminals wanting to speak to each other, we have A wanting to speak with B, and the satellite gateway would make a XOR with A and B, and so we only have to send one packet, one flow to the 2 terminals. So we save bandwidth, satellite bandwidth. The other use case is that one of the main, one of big convergence issue we have in the satellite industry at the moment is the convergence between the broadcast and the broadband networks, which are totally separate at the moment. And with broadband networks, we can provide multicast services, and satellite has huge potential in using more because of its coverage. But the main problem is how you make actually something reliable. And we think that with network coding, we can actually implement some more reliable multicast services. Another one is there's been lots of work on the FEC for the random access links, where basically users don't have to ask for capacity, wait for that capacity to actually send packets. They can actually send packet directly. This is fashion at the moment with all these IoT deployments. And the thing is, this is actually improved, but we think there's still more room for research, because at the moment, systems actually do one or the other. We don't know, we are not aware of system doing actually both of them, like why we could imagine very interesting things that could be deployed, because sometimes there's free capacity that could be used by sending redundancy packets on this free capacity. And another one, but I didn't know you would speak about BATS, but that's not the same BATS. This BATS is a FP7 project, where basically the idea was to try to hybrid the different technologies. For example, today, Eutelsat, when it deploys a satellite service, it may use the 56 kilobytes link you have to send some acknowledgements on some things on the link. And so you don't have a bidirectional access on the satellite link, but you actually use the terrestrial network. So there is here an opportunity to use network coding to actually better, to add some more reliability on the service. And this is more following up on that, because they have done some load sharing schemes, more close to what has been, it's different to what is done by MPTCP, but it's close. And next slide, please. What we need to do next. We need to provide some more details on the SATCOM system. And also, I think there's something that we hadn't mentioned and we want to add is to insist on when we will have huge variations in the satellite capacity. Because some of the use cases we have at the moment are the planes, for example, or all the trains of the satellite constellations, for which there are huge variability, and soon as we have mobile users. So that's what we want to work on, to further detail the architecture to better clarify these use cases afterwards. We think that we still need some work to better match what is done in the taxonomy draft and how we use this taxonomy draft in the description of our use cases. There's still more use cases maybe relevant. Maybe there are some that are actually interesting. We really want to focus on making it happen in the networks. We don't want to make just axis of research that to do many things because there's already been lots of activity on that topic. So we want to be sure about what can be deployed. And speaking about deployment, we think there's a link with what's happening in the network function virtualization working group, because the trends at the moment is that we have all these CRUD RAN activities where we have data centers hosting virtualized functions. This is some trends we see, and we believe that this is a huge opportunity for deployment of network coding schemes on both virtual terminals and data centers. This is still forecast, but that is something we want to look at. And for that, I don't know actually at the moment how it will happen, but we think there's lots of links needed. But I think we need to further work on this document and then see if there's any synergy possible with the ICN document and with what is happening in the network function virtual group. And then we have to see what we remove. First, we add use cases, and then depending on what is relevant, we may add or remove things. So this is it.
Okay, I have a question, Marie-Josée Montpetit. I think I told you I could help on the state of the art. And also, I think what would be interesting in your draft, if you would define what you think is the limits of the satellite network. Where does it start? Does it start at the satellite gateway to the other satellite gateway? Does it start in the networks that are connected to them? Because in my experience, there's different type of losses that are experienced by packets. Obviously, the satellite link itself is usually ultra optimized, so there's very little losses there, but the losses that happen somewhere else. And I think figuring out what the scope of your network is would be really, really important, so that we know exactly where you put the coding and what type of code will be doing the best job.
I think that's very important because for the moment, We have tried to start a description of what is, because nowadays for broadband access, we have multiple gateways in the network. And the problem, basically, we try to match with what the broadband forum is doing in terms of architecture, where basically we have a BNG and then access more access-related parts in the gateway. So we don't have one access gateway, the satellite, and then a door to the internet. We have some network, and depending on what internet gateway manufacturers are doing, loss may happen in the gateway. And also we want to describe that, and that's why we want to detail the mobility use case, because we think that this is the cases where we will have physical layer losses, because the physical layer codes will not be able to cope from these huge variations. Because if we have a fixed broadband network, there's more loss on Wi-Fi than on satellites.
Yeah. One quick question. Yes.
What is the relationship between what you are doing here and NFVRG?
It is just that we think that the problem, depending on the use case and where we put the coding, do we want to put that in the part of the gateway that is actually managing the QoS and the IP packets, or formatting the physical layer packets? Basically, we have different parts on which we can apply network coding, and depending on the architecture, we have lots of functions in these two components, and we are currently working on how we can actually virtualize these components, and then how we think that it's just that the network, it's both basically network coding is the use case for the NFV, and NFV
You want
for
to
us.
virtualize some of those components?
Exactly, we want these functions to be virtualized to ease their deployments in our networks.
Okay.
Sorry for the long answer.
Can I have your name, please?
Shamil Bakuri, YY.
Simon Romano, University of Napoli. First of all, thank you for this document, because I think this is something that is really needed, because as far as I know, there are a number of current projects that are working on this, and trying to find a taxonomy and putting the use cases together is a very welcome effort. I also think that Vincent, who is sitting here, knows about the NFV effort, because I think you had a look at the draft. We're co-authoring a draft together with Professor Angeles Vasquez Castro here, which is exactly about what he was saying. So trying to associate the network coding function with the standard network function virtualization architectures. And just to complete, as a further comment, I'm personally leading a European Space Agency project that is about the use of network coding for content delivery networks in hybrid scenarios involving satellite and terrestrial trunks. And in that case, we are also, I think the nice thing is that we are also trying to sell the network coding part as a means for improving security of the communication, which is perhaps a nice facet to look at. So in case you want to share some information, I would be really glad to do that.
Yeah, I think, thank you.
I will
can have a chat
contact you
afterwards if
perhaps,
you
and
want.
yeah, I think we can also involve
Yeah, sure.
the other projects.
Just for the projects, I'm very interested, because we do lots of caching as well, and I think it's part of the architecture and where you put your data. But for the link for the NFV, our point is not to explain how you virtualize the network, the function, because I think it's more the scope of the NFV working group. But here it's just that we want to focus on how we can actually deploy that in satellite networks today.
Exactly.
And
I
that's
think
an opportunity. It's
yeah.
just that maybe it's just a pointer in the document. Or
Totally agree.
just we want
very
to have
important.
Yeah, to speak about that.
Our project is about a test bed, so we're implementing that. This is a nice thing to do. So it's really deploying the thing, and it's tough.
Thank you.
So very quickly, last question.
Dejan Bogdanovic, are you aware of the delayed disruptive network working group?
Yes.
Because some of, especially this work that you're doing, it would be very applicable for them.
We are working with them, but on other, because of these other historical, because of the CCSDS standardization. So we have a lot of interaction with them for other. It's true that DTN networks is where you could actually apply network coding to actually improve the reliability.
And because they are right now working on some of the data models, to define for the, essentially to define the communication. I had a meeting with them today, and if you're trying to define the APIs for the encoding, while they're working on the data models, you might then have input how they will define it and take this into the account.
Yes, thank you.
Thank you. Thank you.
So hello, I'm Kazuhisa Matsuno from NICT. I made the same presentation in ICNRG working group meeting for thanks for chairs. So I'd like to introduce the network coding for ICN, CCN, and NDN as a use case for network coding for CCN. So we initiated making a draft. So let me introduce the context and content of this draft briefly. Next. Okay. So, network coding has been an attractive research topic. So there are several interesting papers already presented, and so actually last IETF meeting. There are two presentations. One is Cedric-san introduced the overview of network coding for CCN, and it includes content of the InfoCom paper. And Hitoshi-san also presented the network coding for CCN use case for providing the for low latency streaming. And so, we thought we think we need to clarify and specify the requirements and the potential research items for this topic, and they were agree on that. So we initiated making this draft. So actually, ICNRG document describes the network coding related stuff, but it's just simply the benefits. So the purpose of this draft is to provide sufficient information and clarifications, requirements, and challenges in order to establish common understanding this topic and provide useful insight to developers who want to apply network coding into CCN. So here is a proposed structure of this draft as of now. So we introduce current research current research outcome as well as the overview and the overview of network coding and the CCN and architecture. And we specified out of scope. This draft is not to provide a specific solution, but maybe we want to provide a rough solution. Okay, so after definition of both CCN and network coding terminology, we briefly introduce this background, and we will describe the advantages given by network coding and CCN and NDN. And then in the section 4, we'll consider how network coding can be applied into CCN and NDN and its requirement. And after clarifying the requirement, we want to provide the research challenge and the potential research item to make the communication better by using network coding technology as well as CCN and NDN architecture and the protocol. So, network coding brings some benefits such as throughput and capacity improvement and robustness enhancement. So these benefits are not largely different from the CCN and network NDN benefits. So network coding is just focusing on what data to be encoded rather than its data property, such as where it is generated. So it's very in line with CCN core networking layers. So both they are very compatible, and so it's natural to combine them to enhance the key performance system and promote the case for CCN. So yes, and this draft we want to consider how network coding can be applied CCN and NDM network architecture. And then we want to clarify the research challenge to further enhance the CCN and NDM benefits. So here, let me get into the naming requirement. So we have two types of name. One is coded data has a unique name, or coded data doesn't have a unique name. So in the case of the coded data has a unique name, coded data could have a unique name by adding some information, some coding information, such as encoding vector and generation ID, like this. And in this case, consumer need to know the exact renaming structure to retrieve it by using a specific name resolution system. And in this case, also, instead of content producer, content request determines encoding vector. It means that just indicate how to create a coded packet. So other case, in the case that the coded data has no unique name, in this case, coded data, the name of coded data has doesn't have a coding information in the name. So this data may specify the coding information into a meta field and the payload, or in responding to the interest without a unique name for coded data. In this case, node would need prior decoding for generating and providing innovation coding packets.
So I didn't want to bring this up in the ICNRG meeting, but it's relevant here because it's specific to coding. The third bullet there, where you say the content requester determines the encoding vector to be used.
Oh, yes.
Isn't that kind of a separate design decision? Because you could statically decide what the coding vector to be used is by the producer, right? And then you only have one possible, coding vector for all the possible consumers. The trade-off, however, is that if it's the content requester that determines the coding vector, it says that coded packets can't be produced ahead of time. You have to wait until the interest message arrives from the consumer for the producer to actually generate the correct coded packet. So there's some latency and delay implications to having the consumer do that. I would maybe look at that as a separate design answer in the design space, because you could do it either way.
Mm-hmm. Oh, okay. Yes, we need to separate.
You could still have a static encoding vector specified by the producer.
Well, okay. So you mean in the case of the producer and another case is re-encoding. Is it right? Yeah. Okay. So concerning transport requirement, we need to discuss network coding scope. It means that it should be discussed. Nodes can update data packets that are being received in transit. So because of, CCN and the NDN has a mechanism to verify the data integrity. So in this case, re-encoding would require some integrity mechanism. Or another case, another executes network coding only when the received interest for the coded data can be satisfied. It's like end-to-end manner. In this case, it would require a mechanism to ensure full exactly execute network coding. And we also clarify the basic operation at consumer router and the operation publisher, considering the how nodes can provide innovative data packets, especially in the case that coded data doesn't have a unique name. In this case, consumer would need to issue interest with with some coding information for getting exactly innovative data coded packets. And router would need to maintain tally of the interest for spec and generation, and pit aggregation should be avoided for getting a multiple coded data packets. Okay. 2 minutes. Okay. So so in addition to important naming and transport requirements, we'll describe the requirements regarding in-network caching, security and privacy, and routing and forwarding, and how to seamless mobility and their requirements. So as I mentioned that network coding definitely impacts CCN and NDN security mechanisms. So I think we need to clarify these aspects in more detail in the future. So, and after clarifying the requirements, we will clarify these challenges. And in my opinion, I'm very interested in designing how we can applying a sliding or elastic encoding window into CCN, because so the current executive research paper adopts just only block coding manner. So it's a very interesting topic. So that's why now I'm trying to design and implement and evaluation this topic. So I think the next step is to improve this draft from this aspect, and we are going to clarify the requirements and potential challenge in more detail. Thank you very much.
Thank you. Is there any question, comments?
Alison Mencken. So would it seem like it might be that you'll develop a draft here, the draft in ICNRG that cover the two kind of interlocking parts of this? Because that would allow, I mean, I was thinking about the RTC web case, but it doesn't have to be quite as complex as that. No, I mean, it certainly doesn't have to be complex, but I think that getting enough people to look at both things and discuss both things may require splitting the content a little bit. I just throw that out there. I have to unfortunately leave for another RFC editor related thing. So
I think one suggestion would be that the part where we look at the type of codecs, the sliding window and everything is more for here.
yes, exactly.
And the actual implementation on how coding goes into the overall
Yeah. And
ICN architecture could be the other one, but at the end they're the same. They're backing one another.
Absolutely. They're meant to be two halves of the same thing. I just think it would be convenient to identify which things go in which.
And also it would attract different collaborators.
Yes. Yeah.
So I think
So it's, you have all the chairs here, but I invite that discussion.
So this is my ICNRG co-chair hat on, which is, I think the longer we can wait to split this up, the better, because we need cross-fertilization in the community. So the ICN folks need to learn more about coding, and the coding people need to learn a little more about ICN. And at some point, when we go to sort of like move things, you know, really forward, it may be necessary to split it up so we get the appropriate reviews from, you know, the experts in the individual communities. But for now, I think it's going to foster a lot of collaboration to try and not split it up until we have to.
Just get people together.
Yeah.
Okay.
Perfect. Yeah.
That's right. So my name's Ian. I'm one of the quick editors, and I'm going to be talking about forward error correction or network coding in Quick. And it's kind of so last time I talked a little bit about some previous experiments and a little bit of data we had. This time it's more going to be forward looking and saying like, what might be experiments that are worth trying now, and what what approaches architecturally might make sense in Quick. So next slide. Here's an intro into the Quick header in case some of you are not that familiar. The Quick header is pretty small, but it does include a single byte to indicate what type of packet it is, a 8-byte connection ID, and 1, 2, or 4 byte packet number. And the packet numbers are actually truncated, so really the packet numbers are technically 64-bit packet numbers in terms of space, or 62-bit now, I guess, due to a slight quirk. So next slide. Oh, and backwards one, actually, sorry. And the rest of the payload's encrypted. That's all you really need to know. So from the network's perspective, it's completely opaque after that. Yeah. So by forward error correction in Quick, number one is we can, unlike TCP, certainly. Real-time communications, tunnels, maybe multicast someday. As I mentioned at a previous talk, there's still interest in a more efficient tail loss probe, because that's kind of a proactive loss recovery scheme where you don't necessarily have much information and just have to send something, and you're pretty much always wrong when you send something random. That's outstanding. So next slide. Some quick features that may kind of make this mapping a little bit easier and a little bit more tractable from an implementation perspective, at least I hope. One is the Quick's monotonically increasing packet number that increases by 1 every time. I guess I'm hoping that somehow we can utilize this in how we map the coding and describe like which packets are protected by the coding. Multiple flows can share the same 5 tuple if they need to, or you can potentially route like over different 5 tuples but back to the same host using connection ID. So there are a variety of ways basically to say take like 2 flows, and potentially one of them could be a forward error correction flow, and one of them could be the actual base flow as another example, and put them together. And Quick provides multiplex streams which do not head of line block between streams. So a single stream is kind of an in-order sequence of bytes, but we can have up to the 62 individual streams. So there's not a practical limit on the number of streams. So option number one is to put FEC kind of outside the crypto. I guess the way I'm thinking about this option is essentially it is like a separate flow probably. And it goes alongside, and possibly, the packet number of the forward error correction scheme lines up sort of with the original flow. And then there's some metadata inside to try to figure out like how to decode. But this would be somewhat visible from the network's perspective. I mean, you would actually like, presumably for better and for worse, the network could, potentially decode this without having any knowledge of the Quick crypto, right? So like there would be no cryptographic knowledge. As I said, you can use packet numbers. Another pro potentially is this sort of goes on the side. So the standard Quick packetization process would not be modified. So like in some sense, this is like a bolt-on approach opposed to actually like getting inside the core Quick packetization code. Yeah, a con is it is visible in the network. So, I mean, if you care, that may or may not be a major issue. If you aren't doing this end to end, obviously you would need like, some middle boxes, for lack of a better word, to like terminate it in the middle. In some environments, that may be very compelling, particularly since Quick does not, it's not practical to terminate Quick at a performance enhancing proxy. So, there might be cases where instead of running a performance enhancing proxy in the network, your performance enhancing proxy for Quick is, one of these like FEC tunnels essentially, or FEC side flows. So, I mean, I think there are use cases it's practical. It is fairly difficult to integrate into Quick's congestion control. In some cases, it may be actually impossible, which is kind of unfortunate from intellectually, like we'd really like to consider all the bytes that we're sending as part of the congestion control from a bandwidth estimation perspective and like loss detection and all these things. This is completely separate. Yeah, next slide. The next option is to do forward error correction within the encrypted payload. So a pro is that there's no visibility into it. Another pro I should have put is that essentially you can negotiate this, as a unilaterally. So you can say like, I have this new quick option that like you might know about, and the other side says, I know about that too. And, you can negotiate, say, a new frame. So, you could experiment with this without actually minting a whole new version of quick. There is some CPU cost on the con side to coding as well as doing encryption, because you'd be doing the coding inside the encryption. And it consumes an extra byte of payload because you actually have to burn a quick frame type inside the payload. Yeah.
One word question, multipath.
Yes. What about it?
It would seem that there's delicate intertwining with how you add FEC and how you do multipath. Given that Quick doesn't do multipath today.
Potentially. Sorry, given what?
Given that Quick doesn't do multipath today.
Oh, that's certainly true. I mean, I think multipath and forward error correction both at this point kind of fall in the category of things that people are starting to experiment with and understand best, like how to deploy for a post V1 world.
Okay, so my sense is the value of this kind of coding is enhanced significantly in a multipath environment. And sort of trying to put FEC in and then redesign it all over again if it's done before multipath is put in, might lead to either an undesirable situation or complexities that I wouldn't want to consider. So I think we need to think about multipath at the same time we're thinking about coding, particularly this kind of coding.
Okay. Thanks.
I'm Angeles. I'm involved in space agency projects doing network coding, and I fully agree with what he says. And in the other draft, we are dealing with network coding, virtualization. We take network coding as a network function, so then you have to think in advance of all the objectives you want in advance. So it's per flow, multi-flow, per path, multipath. So this is to define a network function before the coding, just for one specific protocol. So this is what we are doing. And I fully agree.
Sure. Oh yeah, no.
I just wanted, Nicolas Kuhn speaking. I just wanted to point out the fact that indeed there's an interaction between the FEC and the congestion control. And this is an open question that we mentioned before, but I think that the link between Quick and FEC and the impact on the congestion control is totally different from the considerations of multipath, for which in Quick multipath, let's say, you will have all these coupled congestion control issues, which are not the same scope. So it has an impact on the congestion control, but not at the same level, in my opinion. So I think.
Yeah. So
I think even though it can be dealt in the same moment when you speak about what impact on congestion control in Quick, in my opinion, it's on the same level because the constraints and the problem you are trying to deal with are not the same.
So I think we're agreeing, but let me check. If you do multipath, it makes large changes to the way Quick does congestion control, independent of whether you're going to do coding as well. Is that what you're saying? Yeah, I agree entirely with that. Yes, if you're going to do multipath, you need multipath congestion control.
Yes, I would agree.
But you can do fake with Quick, and it has an impact on the congestion control. But you may not have. You can have a Quick V1 with that, and do not need to consider the V2 at the moment.
That's also true. I think the point I was making is if you look at previous protocol integrations of coding, they provide modest improvements in a single path environment, but dramatically better improvements in a multipath environment. So from a barrier to adoption and how people will view the value of this kind of work, right? I think people will view the value much higher to bother to do all this work if it's done multipath. So I think we're basically agreeing.
I actually have a follow-up on that. Do you have any references to literature of kind of considerations that they went through and other things that might be relevant? Because obviously since we haven't done Quick multipath yet, and we're just starting to talk about this, it might be a good time just to have those concepts in the back of my mind. if folks would be willing to share. I mean, you can email me later if you want as well.
Yeah, for example, there are several works on the TCP type, so you can see the differences of applying the network coding per flow TCP or multipath TCP. So the constraints and the trade-offs are different. So if you know that, you should consider that in advance. So I still agree with him. So there is this pre-work on multipath TCP that can give you what we are talking about.
Yeah, no, it'd be interesting to read it. Thanks. Next slide. Another option that's. Huh? Oh yeah. I can. I'll blow through the rest. I'll go through the rest, and then whatever remaining time we have for questions, we'll use for questions. A third option that's been suggested is to actually create one or more streams that are forward error correction themselves, and have those protect other streams. So this may work well for existing applications. I know some existing applications actually have mappings that are sort of this form that already exist. You can implement this without any transport changes whatsoever, which is extremely nice. Actually, people have even talked about implementing this in JavaScript, which seems a little bit crazy, but possibly is plausible. Cons is it's fairly application specific, and it may end up increasing the overhead versus kind of on a packet layer just because you're doing it on a stream layer. And yeah, there's no benefit to things like packet number sequencing because you're now dealing with many streams, each of which that have their own byte space. So next slide. My opinion on this so far is that option 2 seems like the most promising and the most straightforward thing to experiment with. It's not clear it's ideal for all circumstances, but it seems fairly flexible, and it's relatively easy to negotiate a new frame type. It should work well with a wide variety of codes. Crypto is cheap, so that negative is really not very interesting. And from the network's perspective, it looks exactly like any other quick flow, which has a nice benefit from making sure that middle boxes don't do terrible things to you. So next slide. I was kind of thought through some of the considerations of how this would interact with something like an API. One of the critical things that we encountered before when we did XOR is that there's always some amount of overhead from the forward error correction and from the code, not just from the code itself, but also from kind of the interaction with the transport and how you do the reconstruction. So it's key to know how much that is, so Quick can kind of leave that amount of extra. Quick does not fragment its UDP packets, so if it needs to leave 24 bytes, it needs to leave 24 bytes. It can't just increase, the coded packets by 24 bytes and have them all dropped on the floor. So it's a practical consideration that definitely needs to be exposed. Obviously, we need to know if it's, the coding rate is dynamic. Can I change it? This is coded bytes. This is more of a non-sliding window case. Number 3 is probably not that relevant, but we might be able to change the coding rate, the length, the window length. And at runtime, obviously, we want to, to add data to be protected, and request coded bytes be sent or produced for transmission. Pretty basic stuff. The challenges and questions are probably more interesting. The first one is the one I sort of went over, which is what do you do about the fact that the coding actually adds overhead? And you need to make sure you actually don't go over your MTU size and have all of your coded packets dropped. Another one is you need to ensure that the code will actually protect the missing packets you're trying to protect. So for example, if you were to use this for a tail loss probe and 2 packets turned out to be lost, ideally you would want to generate another coded packet and then you could, recover both of them. But if for some reason it wasn't a sliding window code, and the window ended, then that wouldn't work, and so there would be no point in trying to generate more coded packets. It would just be trash. So there needs to be some interaction with the loss recovery and the congestion control to say if I generate more code, is this actually going to do anything? Definitely an interesting point. And oh yeah, I guess the last 2. Oh yes, and the other question is does the API need to understand packet numbers, or is there a quick specific shim, or can we use FEC frame, or kind of how is this actually what's the glue with the transport? So given we have a forward error correction API, there's got to be some kind of shim here of how we're going to map this on and everything. So I think that's it. Next slide. Is there one more slide? Okay. I added one slide about implementations. There are now, I think, at least 5 open implementations and probably 10 total implementations of Quick that largely interoperate with each other with TLS 1.3. So if folks ever want to play around with an implementation, they're certainly welcome to try Chromium. But honestly, some of the other ones are a little bit easier to get up to speed with. Particularly the Go implementations tend to be pretty easy to look at if you're familiar with Go. So, I would encourage you to play around with things if you have any interest in this space. And I did send out new slides with the link to the implementations, but it's also on the Go, in the Quick GitHub.
It will be updated. You just have to.
Thank you. Okay, so next is Emmanuel.
So my name is Emmanuel Lochin. I'm working at ISAE Superior in France, Toulouse University. So my talk today is about the joint use of TCP and the network coding layer. So next. So basically, you already presented some part of his work, so I can go a bit faster. So basically what said Vincent at the beginning of this talk is to say that when we are using a network coding layer, we can use it at different level of the DoD architecture. So for instance, above UDP, below UDP, whatever, below IP, this is not a problem. However, when you use it with TCP, you have no choice. You have to be below TCP. And in the meantime, you have to do a kind of cross layer with it. Otherwise, you have to replace the, replace the network coding layer. Oh, yeah.
That's a quick question. So on the patented parts that you mentioned, is the action IPR disclosure?
Yes.
Oh, okay.
Yeah. So you can suppress replace the transport layer by a network coding layer TCP, and obviously there is there is no point to put it above the TCP because there is no point to put it above TCP. Next. So basically there already a solution to replace the transport coded layer, transport protocol layer TCP, which is coded TCP. And the main problem of this implementation is that first, there is one implementation that can be used for instance Linux system, if I remember well, but there is no implementation for all vendors, so you are quite limited and you have to use a proxy-like system or something like that to be able to implement such solution. So next, the idea is simply to use the ECN signal. And the ECN signal is conjointly used with the NC coded layer, network coding layer, and is going to signal to TCP that, for instance, some packet has been masked by the network coding layer, but rebuilt, and to give the information to TCP that there are some lost packets in the network and you have to react on it, okay? Otherwise, all the losses are masked and TCP will never get out from the slow start and you can have some problems because you began to be opportunistic and there is no point to using this protocol anymore. The main advantage is that ECN is implemented in any kind of OSs and they all follows the ECN RFC, I've checked. The main difference is that between them is only on Windows you have to activate it by hand. It's not activated by default. Next. So if I represent how this principle is applied, simply if I consider a network coding layer below the IP layer, and you want to strictly behave like TCP, simply each time you get a decoded packet and this packet is a rebuilt lost packet, you just have to mark the IP ECN bit and transmit it to the upper layer. Next. But for instance, if you don't want to be as bad as TCP over random losses, in that case, you can do whatever you want, if I can say. You can apply a loss discrimination algorithm, machine learning algorithm, any kind of algorithm allowing you to choose to filter some ECN bits and to prevent TCP to react to all losses. Next. No problem to put it above, obviously, IP layer. The only difference is that in that case, you have to mark another field, the TCP field, corresponding TCP field. Next. So just to illustrate what we obtain, I did a simple experiment showing here. So it's a link capacity of 10 megabits. There is an RTT of 40 milliseconds and 2% of random losses. So basically, if I apply the famous Matisse formula, I should obtain something like 2 megabits. That's what I obtain. Next. If I use a network coding layer, so in this example, I use a Tetris implementation, and I do not cross-layer any information to TCP. In that case, TCP is becoming opportunistic, and although all information are masked, so it's going to fetch all the bandwidth available, and this is a problem for the other TCP sharing the same link. Next. On the contrary, if I signal to the upper layer, thanks to ECN, that each time a packet has been rebuilt, I provide an ECN bit to the upper layer. In that case, I have a fair share between both flow. It's not a fair share because it's random losses, but they obtain the same amount of throughput. However, for my TCP tentet, so the one implementing the ECN bit, using the ECN bit, the good put is enhanced as there is no retransmission of packets. So all packets are delivered, there is a delivery ratio which is superior to the standard TCP. Next. And if I use a loss discrimination algorithm or a machine learning algorithm, I have a certain degree of freedom allowing to get more interesting throughput even over random losses. Next. So to conclude, using a CN with a receiver NC layer, so just at the receiver side, allows to simply interact with TCP. There is no modification of existing TCP implementation, and it was the goal to use standard TCP layer without doing a new TCP again coded, and we prevent to check whether we are fair with other TCP layer. And this is compliant with all TCP stack today. Thank you.
Okay, thank you, Manuel. Any questions, comments? No? I want just to clarify, the rate on the y-axis means the good put rate? Or
No, this is a throughput. This is a throughput. I didn't represent it, the good put here. Okay.
José Montpetit, I'm actually presenting on behalf of William Sears from Akamai, and also the support, I acknowledge the support of Brandon Williams. It's actually, we didn't really know.
Closer to the microphone, please.
Pardon me?
Closer to the microphone.
Yeah, I'm close now. I should lower it, I guess. I don't know how these things work. Oh, okay. I'm an engineer, I don't know how these things work. Okay. So yes, we didn't really know at the time what Manuel was going to present, but I guess that we are not really in conflict, because what is in this presentation is basically some of the requirements. And I mentioned the interim meeting that we had in September. One of the main topics that was identified in that meeting as something that we needed to address was this interaction, or lack thereof, between network coding and congestion control. Next. So what we have, and what actually Akamai has measured, and what we all know, is that most of the internet is fairly reliable, but when it's not, we know that the packet loss can be significant. And while there's been some kind of FECX or FEC in terms of repetition code that have been used many years, they actually failed to recover lost packets, especially when these lost packets are not random but arrive in clusters. So you have a series of lost packets. So hence, you don't get any good usage of doing these codes. So this is actually almost a requirement for this whole working group, but a research group. But so we need more structured code, and we've done that. And especially with long RTT, which is the satellite people, it's just almost a conclusion to this whole meeting. The FEC has been shown to shorten the recovery time, and I think this is something that I will send to the satellite people. Next. So what's the problem statement? We do not have to know, or we have to recognize that the use of FEC a lot of times hides the congestion control information that TCP uses, because obviously we correct things. So the packet was lost, we correct it, we send it to the other end. TCP has no idea what had happened in the middle. And there are instances, and actually this is something that's going to be slightly different from what you have said. There are instances where a reduction of bandwidth, the reduction of bandwidth for the Akamai people means that we added some overhead to protect against the losses. And there are some times where this is not necessary. And what do we mean by that? It's very short-term or spiky events that by the time we get the feedback that this thing has happened, it's too late. In any case, there's nothing we could do. So you could actually kind of say we're always going to protect against these things, but then the losses will end up being maybe worse than what you would have done with just living with the spike. Yes, the window will lower, but your retransmission is going to be very low because there's just a few packets that were lost. So maybe it's not worth it. But we all know, and actually this coming back from your presentation, that there are instances where you have more chronic things that happen on almost a regular basis. They're very long term. And again, in the measures at Akamai are very clustered together. They're not, chronic and spiky. But actually, obviously, there's times where both are necessary. And actually, this goes into this idea that maybe we need more than one approach to deal with these different elements in terms of congestion control. Next. So the potential approaches that basically has been done already is that instead of just doing the standard lost congestion control, is actually moved to something like BBR, which is delay or RTT based. And this actually has given some good results, at least in some of the stuff that's been done at Akamai. And it's under investigation. There was this idea of also sending the loss information from the FEC and the congestion to one another. So here's Dave's question.
This may make no sense at all, and it just occurred to me, so just tell me I'm crazy, which is, thank you. In a delay-based congestion control scheme, inaccuracies in measuring delay throw the algorithm off, as opposed to inaccuracies in detecting loss throw the algorithm off. Is it your assumption that the computational cost of reconstruction in a coded system does not increase delay to the point where you're actually biasing the delay as seen by the layer above?
Okay. Actually, we assume that the delay, that one,
the delay of reconstructing packets is really small.
That's exactly what is being assumed here, that the delay in reconstructing packets is very small.
Is that assumption valid?
Yes.
Okay, thank you.
The assumption, it's actually, especially when you start using systematic codes, the cost of reconstructing a packet is very, very low, and will not greatly modify your estimation of the delay. Okay, so the other idea was that sending loss information from the FEC to a congestion control algorithm, like estimate the loss instead of estimating the delay. And then that has been the subject of thousands of papers. How do we define which one is the congestion loss or everything? But we think that this may add a lot of complexity and potential non-standard solution. But again, it's been tried. The other, well, now we know there's the ECN that's been looked at, presented the same segment. The work that was done on trying to distinguish between congestion losses and others, that also has been, this is actually background. And also the work that also Emmanuel presented of MIT and the Hamilton Institute on the TCP/NC and the NC-TCP, which are like the creation of a completely different way of doing TCP with coding. I think at this point, this is not really like a solution presentation. It's actually basically establishing what the problems and where some of the avenues could be. Obviously, Emmanuel presented something that is probably more like a solution. This is like more like an investigation of what could work. I know that Briscoe's not here, but he's not a big fan of BBR, but we were like, we actually thought that actually the delay-based stuff was actually pretty cool for what we wanted to do. So, and Nicholas has a question.
Just, I think BBR is not actually delay-based, such as VGAS could be. It's more that it estimates the channel rate, so it's more a rate-based protocol than properly delay-based.
It's kind of, it's rate / delay /, but it's not.
Yeah, because rate is a function of delay, but
yeah,
it's not the same thing.
Well, well anyway. So yes, I agree with your comment. But what I'm saying is that we think that this first approach of a non-loss based congestion is something that we would like to really look into. Next. So the status, again, we know there's a lot of patented work. We know there's going to be a lot of ongoing work that we would like to report to this group. And the interaction of congestion control and network coding has been the elephant in the room ever since this research group was founded. There was early results that were actually presented in the past, which essentially had ignored the issues of congestion control and essentially were biasing the results incredibly. So that actually is not what we would like to continue. We would like to start looking at new ideas. And we would like to have a draft to be produced either for London or Montreal to start putting ideas and potential solutions and potential architectures into a valid document. And of course, collaborators are welcome. You guys are already working on this. I don't know if you want your own draft, if you want to do something in collaboration. There's probably other people who may have ideas that we would welcome. And what I understand is that William will continue working on these things and will be obviously the main collaborator to the draft. So this was like just a small presentation. Again, at the interim meeting, congestion control was identified as a major issue that the group had to address. More questions? Oh, hi.
Ian Speck, Google. I had a fairly strong opinion on this. So my fairly strong opinion is that forward error correction should always be considered as bytes in flight, as it's usually called in TCP and QUIC when you send it, and you should, whether you're using BBR or any other congestion control algorithm, any packets that are lost or delivered should be treated just like any other packets that are lost and delivered. And so, basically you should be doing congestion control and doing forward error correction, but they ideally should not have any, in my mind, the goal should be they should have no actual interaction. Like that forward error correction or network coding is faster loss recovery. It is not substitute for congestion control. Like if it's substitute for congestion control, I think, so I don't know. I have a fairly strong opinion that if that should be a principle of whatever document. But I mean, that's just a personal opinion. So
No,
I mean, someone could disagree with me, but
I think it's a good comment. But what I'm saying is that if you look back into the history of network coding in general, especially in networks that are TCP based, people were sending a UDP tunnel, for example, in the middle of a bunch of TCP sessions, and then everybody backs off except that tunnel, and then you say, wow, works really well.
Yeah. I totally agree that people in the past have like abused this idea like hopelessly, and that's why I was trying to like put forward that principle.
Yeah, and I think, and for me, I agree, is that if you should be able to show that your solution is not killing the internet.
I definitely agree with your point here. I think this is something really important, and I believe that we have also to consider if one day or another we are going to spread a lot of TCP, NC, or any kind of whether or not redundancy packet, repair packet must be congestion control or not. Mm-hmm. Because if we decrease the TCP flows without considering that we injected a lot of repair packet, it could be a problem. But I definitely agree with this point. I think this is something useful to discuss.
Yeah.
Michael Welzel. My general view on this matter is kind of similar to Ian's, and I at first thought I'm not going to stand up because I don't have any interesting thing to say, because I don't think this is an interesting mix. But I just had an idea, and I want to share that idea. One of the benefits of ECN, one of the benefits is that you can be basically lossless, right? And you have this signal. So in the absence of routers being able to do ECN, there could be a possibility of doing essentially a normal loss-oriented congestion control and just using coding to mask the loss, like not have the loss, right? But you would figure out that it happened, so you could signal back just like ECN would, that there would have been loss. And then you could be in lossless mode and figure out when loss would have happened and when you had to use NC to compensate for it.
And that goes back to the idea of signaling something. And I will tell you that in the past, I've actually looked, when Vincent was talking about the sliding windows and the windows that can grow. Well, the minute that you start seeing your window growing, something's happening and you could start signaling back. So there's a number of these signals that are intrinsically part of what's happening in your queue.
Or you could even use
you can keep them completely separate, but that it's happening.
Or you could even use the ECN feedback, to just signal back on the TCP layer, you signal back CE.
Yeah, that's
even though there wasn't an ECN mark, there just was, network coding having to do what it does.
Yeah.
Right.
So that's why, would you like to collaborate in the draft? No, that's why we think that it's important to have some kind of a document where we can actually capture all these ideas and at least have, like an element to answer to people who say, okay, every time you do network coding, you're killing the TCP congestion control, or you're doing things that are bad for the network, and say, well, by the way, look here, and here are a number of things that can be done and will probably be done to actually do that. Yes.
So a plea, let's not go over again the 30 years of mistakes of not telling the difference between congestive loss and other loss processes. Mm-hmm. We have networks that have other loss processes, and if we simply build something that can't tell the difference between congestive loss and other types of loss, like errors on wireless links and rain fade or any number of other things, we're going to wind up in the same bad place the TCP was for 30 years.
Yeah.
And we may have an opportunity when we put congestion control into network coding, there may be ways to actually tell the difference that we didn't have for TCP.
This is actually has been my holy grail. I think this is why I think it's important for this group to address that problem, so that we do not repeat the errors of the past, and that we can actually come up with, I wouldn't say a solution, but maybe many solutions, but things that will actually work for what we're doing. Okay. Cedric, I think it's yours. 1 second. I know there's some new people who arrived. Would you please sign the blue sheet?
Okay, so this presentation is about some use case of network coding, specifically on a multi-hop wireless network. So I will present one use case. I will present some example of what I think are key feature or constraints that are maybe not found in other settings. And also I will present some example of solution. And the ultimate goal of this presentation is maybe to give some feedback on what is developed in this research group, like module of a generic API. So one motivation, one really timely use case is update of IoT devices. So imagine that you have a large deployment of IoT devices, like wireless sensor type of smart city deployment. And imagine that now you use a medium of short-range radio technology and that you want to update your devices. Then you will have basically to take your firmware image and send it over the air to the entire network. And because it's a multi-hop network, you have to do a multi-hop broadcast. And the thing is also your firmware image is likely to be rather big, so it can be 100 or 1,000 of packets. And if you want to do multi-hop broadcast with a lot of packets, then it's a very suited use case for network coding. And also I want to mention that there are many use cases in general in multi-hop wireless networks. That's why in the different working group, there have been protocols that have been proposed to do broadcast and multicast, like in ROR or in MANE. So now one specific thing in a multi-hop network is you really want, when you want to do broadcast, is that you really want to use the wireless multicast advantage. It's the fact that when you transmit one packet, you have many receivers. And most of the protocols, they do optimization in one way or another on the fact that you can have some kind of subset of a node, like represented on the figure on the left. That's the black node. Only them will transmit the packet. And if you select properly this subset and if everything goes well, you have an efficient wireless broadcast. Now, this works well when sending in open loop. The problem is now if you want to have some feedback. So for instance, you cannot do acknowledgement on every received packet because you will use the wireless multicast advantage. So you don't want to do that. And then you have a really problem. It's not straightforward to design an efficient control plane where you are able to say that your broadcast is working well. So to address this problem of efficient control plane, some protocol have been designed. So that's DragonCast, DragonNet. There is a draft. There is some implementation. And this protocol have been proposed by various people at INRIA. And they are based on two principles. The first one is network coding used. We are doing broadcast. And then every node in the network sends coded packets. So it participates in the network coding process. And also what goes with this is the fact that the state of a node is piggybacked on each coded packet. And this is a way to have knowledge actually of the state of a neighbor. So it's a kind of a local control plane. This is the first principle. And the second one is that the protocols act locally. And by acting locally, this is still sufficient in most cases to ensure that the broadcast is working well globally. And they act locally in this way is each node try to help the neighbors. So it increases its rate if a neighbor is falling behind. So that's the Dragon module. And also it generates a proper packet, that's the SU module. So this is a more detailed view of the protocol, but basically on the left you have one transmitter which has some decoding buffer with some coded packet, and what is important is the state. The state is it has decoded 2 packets. He has a rank 3 in the decoding buffer, and he has a window which include a decoding buffer, which include source packet 3 to 6. And when it sends the packet, as I mentioned, it will add in a header, along with the coded packet, it will add the state, and this is received by the neighbor, and this is stored in a neighbor information set. And now how it is used is described on the next slide. It's the sliding encoding window module. And what the node do is take the neighbor information set, look at how many packets each neighbor has decoded, and then the node help the node which is the most behind the decoding process. So on the figure, you have node B, which has decoded only up to source packet 9, and then the generate coded payload will start with source packet index starting from 10. So that's the principle of the protocol. And now, if we want to connect this to the generic API description, so it's on the next slide. If we want to see where the generic API module will be, it will be in the sliding encoding window. It's not clear entirely where it will be, but there is at least this part, which is the decoding buffer, which is the library that also Vincent mentioned, which does basically inner coding operation and maintain a decoding buffer. And so the decoding is easy. Every time a packet is received, it is added in the buffer, and potentially one step of Gaussian elimination is run, and potentially one decoded packet is handed back to the application. And then on the next slide, we can see that the coding part is more complex. The coding part is more complex because you need the neighbor state information, which is sort of rather dependent of the protocol. And you need to use this state information to extract or to generate the proper packet to help your neighbor. And this is where maybe there could be a discussion for the generic API, for instance, because here the constraints are minimum index and maximum index, but there could be others. And I want to insist on the fact that here the neighbor state information is not even in the coding module, because it's dependent on the protocol, which depends on the use case. If you are doing a network coding point-to-point, maybe it will be more easy to get this state, because it's the state of the other side. But here, this information is not necessarily even accurate, because you can lose packets, but it works. And then on the next slide, yes, this is what I was discussing. So maybe the generic fake API will be something around this module. If for this use case, so if there is a generic fake module which is designed in this group, it will be there, and the use case will use this in this kind of way. And the last slide is just to mention that if you change slightly the hypothesis, like if you allow node to be desynchronized, then probably you need difference lining and more general encoding strategy, buffer management. So you need some flexibility. There is a discussion in an expired draft, but it's just to say that things are not always straightforward. There is maybe not always a single solution. And yes, that's conclude my presentation. And if there is some comment or question, I will be happy.
I just have a question on how you select the repeaters. Does it follow a stochastic process, something like that?
Yes, it's a kind of stochastic.
It's a random walk?
Not really, because every node is repeating coded packet. It's just that every node waits for a random time. And so this is the packet rate, basically. And the packet rate is adjusted dynamically, depending on the state of the neighbors. So if you have a lot of neighbors that are late in the decoding process, use on more packets.
Ah, okay. Thank you.
Vincent Walker. Question: how far do you think your libLC, I think this is the name, yes, libLC, is specific to your use case or generic? I have in mind the future works
Yeah.
on shared open source codec.
So how much is specific? I don't think it's really specific. It's just the fact that it assumes Gaussian elimination, which is done online. But on the other hand, it's not the whole protocol. It's just one specific part doing the decoding and only offering feature to do coding, like adding packet. So it's fairly generic, but some things are missing to do a complete protocol. Of course, but.
And next question on this work, what is the future?
So this
what is the status?
So it's a really preliminary version that has been cut and passed and just compiled. So the next step is to clean it up and also probably to try to release the entire protocol for wireless sensor network for the use case at least of broadcast, and maybe over-the-air update. But that's not the immediate goal. That's maybe not done immediately, but yes, at least clean up this library.
Thank you. So we still have 5 minutes. I don't know if somebody wants to bring a question, a comment, or otherwise we can finish now.
I don't have any comments. I think I'd like to thank everybody.
Yeah.
For everybody in the room, I think from all the meetings I've been attending of this working group, I think this has been the most productive one and the one that has been the most discussions and great presentations. I would like to thank really, really everybody who came and actually participated, and I would encourage you to continue participating. I think there's great stuff we can do with this, like Dave said. We can actually start doing something about, the errors in this thing. We can start having real protocols. We can start having really good implementations, and your help is absolutely needed. And again, thank you so much for everything you did.
Yeah. Good conclusion.
Thank you.
Thank you.
Awesome.
Thank you.